So as promised, we're going to do a problem set question related to buffers in class. So this is from problem set 19, question 15.43. How do I know that this solution that I'm making is a buffer? Calculate the pH of a solution with 0.5 molar CH3NH2 and 0.7 molar CH3NH3Cl. How do I know this is a buffer solution? Adam? One is an acid and one is a base. They're a conjugate pair, but they're a little bit masked right now. What do I need to throw away before I can see the conjugate pair? All right. Cl minus is the conjugate base of a strong acid, so I can say it's going to be a spectator ion and just change this to CH3NH3 plus. So I have CH3NH2, weak base, CH3NH3 plus, it's conjugate acid. So I have a weak acid, weak base, conjugate pair. I recognize that as a buffer. All right, what has my approach been pretty consistently when I want to find the pH of a solution? Rice, all right. Now, I can think of a couple of different approaches here. I need to write an equilibrium that has both of these species in it. Can you think of an equilibrium that will contain both CH3NH2 and CH3NH3? All right, so one approach is to take the acid dissociation equation for CH3NH3 plus. What would another approach be? Another approach would be to use the base equation. So there I would do my Rice chart with this reaction, CH3NH2 plus water makes CH3NH3 plus, I ran out of space, plus OH minus. Now, I wrote that small and off to the side because while it would work, why would it be slightly more work to use that approach? Because that would give me concentration of OH minus, which would then give me POH, which would then give me pH. So it would just be an extra step. And I have to write the water to balance the equation. It's just more work all around. So I'm not going to do it that way, but it would work. It would be fine if you did. All right, go ahead. Fill in your initial concentrations, your change, your equilibrium. Think about how you're going to solve for pH. All right. So first confession, I definitely didn't leave myself enough space here. My apologies for that. All right. We got x equals 3.22 times 10 to the negative 11th. That's the concentration of H plus. Oh, 3 point. Okay. So we have some people saying 3.196, some people saying 3.2 something. It's all going to be close enough. Now, if you put it in your calculator, if you take the negative log of 3.22 times 10 to the negative 11th, and then take the log of 3.19 times 10 to the negative 11th, go ahead and do both of those calculations. They turn out to be basically the same number. So I'm not really going to worry. pH is going to be the negative log of that. Like 10.49, 10.50, something like that. All right. All right. Is there a shorter way I could have calculated this pH? Yes, as soon as I recognize that I have a buffer solution, I can just use that Henderson-Hasselbalch equation. So I could have, in theory, just as soon as I recognize this, said, okay, pH equals pKa plus log of conjugate base over acid. So I would calculate the pKa, which in this case, if I remember, turns out to be like 10.65. So it would be the negative log of Ka. All right. So 10.65 plus the log of base form, which was 0.5 over 0.7. So again, I'd get 10.5 there. Oops. Question. Student question is, where did I find the pKa value? The pKa value I got from taking the negative log of Ka. So this here was negative log of the Ka, which was 2.3 times 10 to the negative 11th. So you had to figure out that Ka value, which I did down here at the bottom of the screen. So this is why, problem set 17 kind of gave you a bunch of practice of finding Ka if you only know Kb of the conjugate base, right? These are things you're going to need to be able to do fluidly in order to solve problems. Other questions? All right, we have the pH now of this buffer solution. What the next part of the question is going to ask us to do is think about what happens when I add a strong acid or a strong base. How does the buffer actually work numerically? So the next part of the question is calculate the pH after 0.1 moles of NaOH is added to 1 liter of the solution in exercise 43. All right. So I think the handouts actually said problem set 21 because That's what it used to be. So that's why I crossed it out up here. So the first question we need to ask ourselves here is, what happens when we add NaOH to our solution? Which part of NaOH am I really concerned with? The OH minus, right? I'm really just focusing on OH minus. So I add OH minus to the solution. And OH minus, this is a strong base. Bases look to do what? Take H plus. They want to take an H plus from somewhere. So OH minus looks around and says, who's the best thing to take H plus from? CH3NH3 plus. So now I'm going to get a reaction where OH minus goes and grabs H plus from CH3NH3 plus. Remember last time, what we said was the role of the weak acid in a buffer is to react with any base that you add. So this is the reaction that's happening. Now, the next question is, does this reaction happen a little bit? Does it happen a lot? How can I tell if a reaction is going to happen a little bit or a lot? Find the K value. So the question is, what is the K value for this reaction? Because that'll tell us, like, okay, how much, to what extent does this reaction happen? Does this equation look familiar? All right, it's an acid-base reaction. Does it look like an equation we would write for Ka? No, why not? An equation we write for Ka would have what in it? H plus. This equation has no H plus in it. So it's not a Ka. Does it look like an equation for Kb? Well, it sort of looks like a Kb equation because it has OH minus in it. But in a Kb equation, OH minus would be a product. This equation is actually the reverse of the Kb equation. So when I reverse an equation, what's going to happen to its K value? Remember, in general, K equals products over reactants. If I reverse the equation, what am I doing with products and reactants? Switching. So I'm taking the reciprocal. So the K value for this reaction is actually going to be 1 over the Kb value. So the K for this equation is going to be 1 over that Kb, which we looked up a minute ago. It was 4.38 times 10 to the negative fourth. So now that's going to be 2.3 times 10 to the positive third. All right. How would you characterize that? It's big. All right. When we have a really big K, what does that tell me? This reaction goes to completion. All right. Very big K tells me the reaction goes to completion. part of what you're going to do on problem set 19 is look at a bunch of reactions like this where you're reacting an acid with a base, and you're going to come to the conclusion that pretty much in every case where we react an acid with a base, you end up with a really big K value, and so the reaction goes to completion. But I force you to do it on problem set 19 so that you really internalize it. You're going to do it over and over until you see it and say, okay, yeah, every time I react a strong base with any acid or a strong acid with any base, the reaction will go to completion. So now, how do I use that to answer the question that's asked? Well, I can do a Rice chart. There's really two approaches I could take. So I'm going to do a split screen here. Oops. One approach is going to be to do the long Rice chart. So anytime I know the reaction goes to completion, I can do the long Rice chart. And actually, let me be more specific in the middle. What the 3 C's mean. I have initial, change, completion, and then change back. So I could do this with the reaction as written. So the reaction we just wrote was OH minus plus CH3 NH3 plus makes CH3 NH2 plus water, which I don't really care about. So I'll work in moles per liter. What's the initial concentration? What are all the initial concentrations that go in here? All right, 0.1 OH minus, because that's what I just added. 0.7, because that was how much conjugate acid was in the buffer. And then 0.5. So if this reaction is going to go to completion, what am I going to run out of first? OH minus is limiting. So this is going to go down by 0.1 to 0. This will go down by 0.1. And this will go up by 0.1. But of course, I can't actually get to 0 OH minus in my solution. Right? The reaction is going to come to equilibrium. That's not actually going to be 0. So I have to send it back a little bit. When I send it back, this goes down a little bit. This goes up a little bit. So I get X. Now when it's coming back a little bit, 0.6 plus X will be around 0.6. 0.6 minus X will be around 0.6. So now I could use the K value that I just calculated to solve for X. sorry. So I set up the equilibrium expression with this equation that I just wrote. I plug in my values, solve for x. X represents what here? Concentration of OH minus. So I can get POH is the negative log of concentration of OH minus, which would be the negative log of 4.38 times 10 to the negative fourth. .36, so the pH equals 10.64. All right, so I added 0.1 mole of hydroxide and the pH went from 10.5 to 10.64. Is that a huge change in pH? Not huge, no. Little change in pH. There's an alternate approach here. I could have cut myself off earlier. Does anyone see where I could have cut myself off earlier? All right. So an alternate approach is to stop at the completion step. Because I still have a buffer solution at that point. I still have a weak acid, weak base conjugate pair. So at that point, I could just apply the Henderson-Hasselbalch equation, HH equation. Maybe we'd miscalculated 10. I said pKa earlier was 10.65. Is it actually 10.64? Not that it makes a big difference. But what is the log of 0.6 over 0.6? All right, what's the log of 1? 0. So we'd get pH equals 10.65 or 10.64. For consistency's sake, I'll change them all to 10.64. The question is there some sort of law or rule when you have equal concentrations of conjugate acid and conjugate base? Yeah. When you have equal concentrations of conjugate acid and conjugate base, the pH will equal the pKa. So that we could have just done that. Yeah, so we said that the first day we're going to run into this a lot when the pH equals the pKa. Then, when the concentration of acid and conjugate base are equal, pH equals the pKa. So yes, you could have also done that as a shortcut. Said, oh look, I have equal concentrations of acid and conjugate base. pH equals pKa. So the question is, do you still have to do the Rice chart first? Yeah, I mean, you want to keep track of, if you send it to completion, what happens to the concentrations of each thing. Now, some people may be able to do that in their heads, right? So some of you may be able to say, oh, I'm going to lose 0.1 molar of CH3NH3+, and I'm going to gain 0.1 molar of CH3NH2. And that's okay if you can, but I always write it out. I always like to keep track on paper. You'll find as you get older too, your brain gets faultier, and it's just much simpler to have it written down. You can essentially copy it onto the problem set. Yeah, the question was, if I took this down on my notes, can I copy it onto the problem set? I believe there's a second half to the question that we're not going to do here. So if you don't want to copy all the work for the first two parts, that's fine. But then you've got to do the work for the third part on the problem set. So we want to compare the buffer to pure water. We said for the buffer, when 0.1 mole of NaOH added, pH goes from 10.5 to 10.64. Okay. Now let's think about pure water. You can do this calculation. If 0.1 mole of NaOH is added to 1 liter of pure water, talk about it at your table. Okay. pH of pure water is pure is 7. After you add 1.1 mole of NaOH to a liter of it, how do you get the pH? So 0.1 mole of NaOH means 0.1 mole of Na plus and 0.1 mole of OH minus. So the concentration of OH minus in the solution would be 0.1 mole over 1 liter. So the POH would be the negative log of 0.1, which is 1. And the pH, 13. All right. So for the buffer, it went 10.5 to 10.64. We do the same thing to pure water. It goes from 7 to 13. That's the power of a buffer. It keeps the pH in a relatively close range. Whereas pure water does not. What questions do you have? So the question is, does that mean that the OH minus ions actually remove protons from the water molecules? And the answer, this is very similar to a question that came up the other day, and I'm glad it came up. Let's think about it. OH minus plus H2O. If it removes a proton, what does OH minus become? H2O. And the water becomes OH minus. So the answer is yes, it does, right? But it has no net effect. So this proton exchange is happening a lot in that solution, but it has no net effect. This question came up the other day when we were talking about when we introduced the idea of buffers. Came up in regard to HF and F minus. So would those two react in solution? And we said yes, they will, but it has no net effect. Same thing, OH minus ions do take protons away from water, but it results in the same thing. All right, so our buffer was really effective. It didn't allow the pH to change by very much. So if you needed a solution to keep its pH right around 10.5 or 10.6, this buffer would be a great choice. But the question came up last time, is that indefinite? Could I just keep adding more and more and more base and the buffer will never change? And the answer is no. There's a concept called buffer capacity. Buffers don't work indefinitely. If you add enough acid or base, the buffer will stop working. So the question is this like heat capacity? Not exactly, because heat capacity is a continuous thing. So heat capacity allows you to say if I add X numbers of joules of heat to an object, how much will its temperature change? And if you add less heat, you know, the temperature change will just be smaller. If you add more heat, the temperature change will just be larger, but it's proportional. With a buffer, what we find is there's a threshold. And if you overcome that threshold, the pH will change wildly. And we'll do a calculation to show that in a minute. I always forget. Threshold, 1H. So every buffer is going to have its breaking point. So it has a certain capacity, and it works. And beyond that capacity, it fails. Instead of being like heat capacity, probably a better analogy would be like the weight capacity of an elevator or of a boat. You know, you have a boat with a certain weight capacity. You keep adding weight to it, and it's under capacity. You know, it goes down a little bit in the water. But you get over capacity, and suddenly it sinks. So I think that's probably a better analogy. So let's look at this phenomenon for ourselves. What happens to the solution that we were just talking about if instead of adding 0.1 mole of NaOH, we add 0.8 moles of NaOH? So go back and think about our setup. We had set up a Rice chart. We sent it to completion. So let's do that. Let's send this reaction to completion. All right. So now my initial concentration CH3NH3 still 0.7. CH3NH2 still 0.5. OH minus is now 0.8. How is this definitely different from before? Yeah, before OH minus was the limiting reactant. So since OH minus was the limiting reactant, I used up all of it. In this case, what's the limiting reactant? CH3NH3 plus. This is now the limiting reactant. Remember, a product can't be a limiting reactant by definition. So CH3NH3 is my limiting reactant. Now minus 0.7 plus 0.7 minus 0.7. So when it goes to completion now, what I'm left with, is this a buffer solution anymore? No. What I have now is a mixture of strong base, OH minus, and weak base, CH3NH2. Much different from before. So this is no longer a buffer, and I don't even need to do anything else to calculate the pH now. Because what species in the reaction is important to calculating the pH? OH minus. And I know the concentration of OH minus because I have some left over. So POH is going to equal the negative log of the concentration of OH minus, which is going to be the negative log of 0.1, which is 1. So the pH will be 14 minus POH, which is 14 minus 1, which is 13. So we have overcome the buffer capacity now. We made our buffer cry for mercy and break. So the question is, what if it were just under the capacity? So you can actually, test these things out a little bit. All right, I have a blank slide here. All right, so we have a couple of data points now. We know when we have 0 moles of OH minus added, it was 10.5. When we added 0.1 mole, it was 10.65. 10.64. Yeah. Just for consistency's sake. Okay. And then we knew when we added 0.8, now the pH was up to 13. So the question is, where along there is the breaking point? The calculations for 0.2, 0.3, 0.4, 0.5, and 0.6 would actually be relatively straightforward to do. And the reason is we can use that shortcut where it's just pH equals pKa plus the log of base over acid. So if it were 0.2, for example, to do the 0.2, I'll do it in green. Without writing out the Rice chart, this is 10.64 plus the log of, all right, if my numbers had been 0.2, without writing a new Rice chart, CH3NH3 plus would have gone from 0.7 down to 0.5. CH3NH2 would have gone from 0.5 up to 0.7. So there it would have been 0.7 over 0.5. So you can calculate that number. Go ahead, feed me that number. $10.79. And then, if we want to skip down a little bit, let's see what it would be at 0.4. There, pH would be 10.64 plus log of. Now, if that had been 0.4, CH3NH3 goes down to 0.3. The numerator is going to go up to 0.9. So that would be 11.12. All right, so still climbing relatively slowly. What we would find if we continued our calculations is the jump would occur, the big jump would occur between 0.6 and 0.7. Right around there is where we would find the biggest jump. We've already answered this question, actually. One qualitative question we might want to answer is like, does a specific buffer have more capacity against acid or against base? What that's going to depend on is there more weak acid or weak base in your buffer? So in this case, which was there more of? Weak acid. So this is actually going to have better buffering capacity against bases because there was more weak acid. So, this had the capacity to buffer against somewhere up to close to 0.7 moles of base, but only up to 0.5 moles of acid being added before it would overcome the capacity. All right. Any remaining questions about buffers? So the question is, like, how do you choose a buffer system to use? So to choose a buffer system, there's a couple of factors. One would be, what is your target pH? And you usually want to choose a buffer system that has a pKa near your target pH, because we can see from the equation that the pH of the buffer is usually going to be around the pKa of the acid. And then the second would be, depending on your application, you want to choose things that aren't going to be harmful to other things going on in your solution. So for instance, if you were making buffer solution for contact lenses, you would want to make sure there was nothing in there that was going to irritate or react with your eyes. If you were doing biological a solution for cells to grow in, you want to make sure it's not toxic to the cells. So, those would be the considerations. All right, titration tomorrow. Yes, you're doing the lab tomorrow, titration lab. Yeah, so tomorrow lab, more lecture next week.